So first a favor, which is, does anyone have an iPhone charger that I could borrow for the duration of the lecture? Thank you. Second, as Carol noted, I'm engaged in a bit of shameless self-promotion. So I am very excited about the use of linear programming techniques in the analysis of mechanism design. So I put some of that into a monograph. Here's what the monograph looks like. And for those of you who think ideas sell themselves, you're mistaken. That's why you have to promote. If some of you have read the book on matching by Roth and Sotomayor, there's actually a very important line in the introduction which is worth remembering, which is Columbus's discovery of America is important not because he was the first, but because he was the last. And the same is true in science. Many theorems have been proved, many important theorems have been proved more than once, but the name of the theorem is usually given to the last person to prove it. Okay? And I'll use the word shameless a second time in the talk, and I'll also let you know when that occurs so that you'll see just how little conscience I have. Okay? So for today, I want to talk about the use of shortest paths and the use of a method known as iterative rounding in mechanism design problems. Okay? So to illustrate the use of shortest paths, I'm going to look at Meyerson's classic result on optimal auctions and a lot of the machinery we've already developed. Now, you will see a discussion of Meyerson's optimal auction in Jason Hartline's lecture. But Jason will focus on the case of continuous types. I'm going to assume discrete types. But once again, whatever you see in the discrete case, by taking appropriate limits, you can get the continuous. Okay? So there's a single good to be allocated to agents so as to maximize expected revenue. So in this world, transfers are permitted. I have n risk-neutral agents. The value of each agent for the good, again, I'm going to call their type. That's their private information. As before, I'm going to assume types are drawn from 1 up to m. F sub t is the probability that a buyer is of type T, and types are drawn independently. And capital F is the distribution function. And here's a new thing which I didn't have yesterday, nu of t, which is to the type minus this object. And this whole thing is called a virtual value. And sometimes it is common to impose an assumption on the virtual value, which is that this object is monotone. And that's known as the monotone hazard condition. Okay. So just to remind you, if I'm in this case, a direct mechanism will consist of an allocation rule and a payment rule, because I'm allowing transfers. Again, focus on the allocation rule. So an allocation rule should really be a map from the profile of all the reported types to a probability of you getting the good. Now remember, I'm focusing on direct mechanisms, so the only thing an agent is allowed to do is report their type. So that's why the allocation rule only needs to be defined on the profile of types. Now, as before, I don't really want to work with the little a because there are too many of them running around. So instead, we work with the calligraphic a, the interim allocation probability. Yes?
Just one thing. What is regular then? Regularity?
So the regularity assumption is just that the monotone hazard rate condition holds.
So it's the same thing?
It's the same thing, yeah.
Okay. And is that different from MHR?
No, it's the same thing. So in other words, yeah. So the MHR is usually defined in terms of saying something about the monotonicity of this. Regularity says that this is monotone. Okay. Okay, so I'm looking at I'd rather work with the interim allocation probabilities. And just to remind you, in the case when the allocation rule we're looking at is symmetric, doesn't depend on the names of the agents, and I'm going to assume that's the case here. We have the following characterization to Borda, Maskin, Matthews, and Riley that says a collection of calligraphic A's is implementable, corresponds to an allocation rule, if and only if they satisfy these inequalities. And remember, this object over here is submodular, so what I've got here is essentially a polymatroid. Okay? Okay. I want to maximize expected revenue, so there's my objective function. F sub t is the probability that an agent is of type t, and I've multiplied that by P sub t, which is the expected payment that an agent of type t is going to make to me. Okay? Notice I've not multiplied the objective function by n, the number of agents, because that's really not going to make a difference to the solution. So the objective function, if you like, is the expected per capita revenue. Okay? Now, what are the constraints? Well, I have to choose allocation rules that are feasible, so that's encoded here. I have to satisfy individual rationality. So if you say you're type T, this is the expected quantity of the good that you receive. This is your expected payment, and this has to be non-negative. Notice where I'm using risk neutrality, because agents only care about their expected payoff. Right? Now, I need this constraint to prevent the problem from being trivial, because in the absence of this constraint, I simply charge everyone their firstborn and walk away. Right? The top constraint is the incentive compatibility constraint. The left-hand side is your expected surplus if you're type T and you truthfully report that your type is T. And the right-hand side is your expected surplus given you're of type T, but instead you report type S. If you report type S, you get the allocation intended for the person whose type is S, and you make the payment intended for the person who says their type is S. Okay.
Sorry, just to be clear, the P's here are...
The P's are expected payments. Right. Okay. And the reason, and this is where I'm using the risk neutrality, I don't care about your realized payment, I only care about your expected payment. Okay. Okay. Now, this is not quite a polymatroid optimization problem because the objective function is in terms of the P's, but the P's don't appear anywhere here in the polymatroid. But you will notice that the P's appear in those incentive constraints and the IR constraint. Okay? One additional thing I'm going to do, it's minor. I'm going to introduce a dummy type called type 0. And the advantage of doing that is I can throw away the individual rationality constraint and just have incentive compatibility constraints. So now when you look at the type space, remember the types include this dummy type. So if you announce the dummy type, that's another way of saying I'm walking away. Okay. The P's are linked to the A's. Now, if you look at those inequalities above, and let's take a high-level view, looking at those inequalities, you know there has to be some relationship between the P's and the A's. Okay. What's the form of the relationship? Well, the P's will have to be some piecewise linear function of the A's. That's just from the property of linear inequalities. Okay. So in principle, you could take that piecewise linear function of the A's and stick that into the objective function. So at a high level, what's the problem? It's maximize a piecewise linear function subject to a polymatroid constraint. Now that piecewise linear function will also happen to be concave, so you're maximizing a piecewise linear concave function subject to polymatroid constraints. Now this we know how to do. There's a similar greedy algorithm. Pick the variable whose objective function slope is as large as possible, make it as big as you can until its marginal value is equal to some other variable, and then push that one up. Right? So in principle, you could do it that way, but the problem here is there is no explicit description of the objective function. The linear segments in that piecewise linear function, that piecewise linear concave function, are given implicitly. So any algorithm you use would then have to figure out the segments in addition to optimize. Okay? Now, it is not obvious in general how to do this in an efficient way, but I think Kostis will say something about that later, right? Okay? So I will leave that to him. In this particular instance, it turns out there's an easy way to do this, because in this particular instance, it turns out that you can write the payment functions as a linear function of the calligraphic A's. Not piecewise linear, but as a linear function of the calligraphic A's. Now, because the little p's will be linear functions of the calligraphic A's, when you plug them into the objective function, you have a straightforward maximize a linear function subject to a polymatroid. Yes?
Sorry, so you said it's expensive to maximize the objective when you have piecewise linear constraints. Would it be any cheaper if you did the reverse and substituted the cursive calligraphic A's in the polymatroid cookies?
So you mean eliminate the calligraphic A's in favor of the little p's. So
then your objective function is still linear, but you have a piecewise linear polymatroid.
all right, okay. So the answer is, in principle, that's doable, and there are examples where, for some, not this problem, but for other problems, where people have found it more convenient to work with the p's rather than the a's. But I don't know of too many examples where that turns out to be successful. Okay, but I'm not going to rule it out. Okay, and actually, when you plug, if you eliminate the a's in favor of the p's, it's not clear what you get over here, right? So I don't know whether that's a well-behaved polyhedron anymore. Okay. Okay, so what I want to do is look at the incentive compatibility constraints a little more closely. So let me step back from this and now talk about the shortest path problem. So the shortest path problem should be familiar to many of you. Let's do a simple one. I have a source node. I have a sink node. Each edge has a length, and I've written those lengths down next to each edge. And your goal is to find the shortest path from S to T. It's a well-defined optimization problem. And you can set it up as a linear program by simply rephrasing it in the following way. Find the minimum cost flow of one unit of a divisible good from source to sink. Now notice, by saying that the good is divisible, that allows me to set it up as a linear program. So I could potentially send a quarter of a unit of flow along one path, a quarter of a unit along another path, and half a unit along some entirely different path. But if my goal is to minimize the total cost of flow sent, it's obvious that if there is a short path, I want to send all the flow across that. Okay? Now, is it the case that this optimization problem always has a well-defined solution? The answer is no, which is, suppose instead this edge had a length of -7, then the problem of finding a shortest path from source to sink would not be well defined, because if you phrase it as sending a unit of a divisible good from source to sink so as to minimize cost, what would you do? In other words, the linear program would have an unbounded objective function value. For any number you pick as small as you like, there is a solution which yields an objective function value smaller than that. Does that make sense? Okay. So if there are negative cycles in this problem, then the objective function value is unbounded from below. Okay? Now, it's not hard to see that if there are no negative cycles, then the problem is well behaved. Does that make sense? Because if you're looking for a shortest path from source to sink, you clearly cannot gain by going around a cycle if every cycle is of positive length. Okay? So first observation is, in the absence of negative cycles, the problem of finding a shortest path from source to sink is well defined. Now, it's worth writing down the dual to the problem of finding a shortest path. And actually, on this slide, I was just setting it up what a linear program might look like. That's not really interesting. Here's the dual. I'm maximizing yt minus ys, so that means for each vertex I have a variable, which is typically called a node potential, And here are the constraints. Yi minus yj is less than or equal to Cij. High-level view is to see why this is plausible. The primal problem was find a minimum cost flow. So the primal problem is a min, therefore the dual problem should be a max. In the primal problem, you're looking for a minimum cost flow. That means the objective function must contain theCij's. So when you flip from the primal to the dual, whatever's in the objective function goes down to the right-hand side. So you've gotCij's over there.
So what
Now,
is the interpretation of the Y's? What is it?
I'm going to give you a couple of interpretations in a moment. Okay? One other observation I want to make is the following. If you give me a solution to the dual, adding a constant to every variable doesn't change anything. Add 5 to every y, nothing changes. Agreed? Okay. Now what that means is I can always normalize the ys to be 0. Right? Because just choose your constant. So give me your favorite solution. Now choose a constant to make ys 0. Now, when you solve the dual, what's the interpretation of these y's? These y's at optimality will represent the length of the shortest path from the source to that vertex. Okay? Now, in a sense, you shouldn't be too surprised, because those of you who have looked at algorithms for finding shortest paths from sources to sinks would have noticed the following. If you set out to find the shortest path from a particular source to a particular sink, for free, you get the shortest path from that source to every other vertex. So you might puzzle over why am I getting more than I asked for? Well, the reason you're getting more than you've asked for is that if you have an algorithm that determines the optimal path, it must come with it a certificate of optimality. That certificate of optimality is just the dual. And the dual variables, as I said before, represent the optimal values of the dual, represent the length of the shortest path from the source to the sink. Okay. Now, what I care about for the moment is this system here is feasible. So I don't care about the objective function. This system here is feasible if and only if there are no negative cycles. Why is that? It's the usual result, which is the primal is bounded if and only if the dual is feasible. We just argued that the primal is bounded if and only if there are no negative cycles. So therefore, the dual system is feasible if and only if there are no negative cycles. Okay. Now let me give you two interpretations of the y's, one physical and one economic. For the physical interpretation, what I want you to do is to imagine a structure which has a string for each edge and a ball of unit mass for each vertex. And then take that contraption, hold it up by the source at some sufficiently high distance above the ground, and interpret y sub t as the distance from the origin, and the origin is up here. Now, how should this system of strings and balls arrange itself? It should arrange itself so as to minimize the total potential energy of the system. Okay, so what's the problem of minimizing the total potential energy of the system? It's that. Right? Because the vertex T should occupy the lowest possible position. That's the max yt. Okay? And everything else is constrained to lie by the lengths of the edges that are going to it. Okay? So one interpretation of the y's is that they're potential energies in this particular physical system. Okay? And so what the condition says is that in the absence of negative cycles, this collection of balls and strings will organize itself into a stable way. Now, if there's a positive cycle, you can interpret that as basically saying you're generating energy out of nothing. Second interpretation, think of each node as a city in which a homogeneous good is sold. The same good is available at all the other cities. And the yi's represent the price that you pay to purchase the good in city I. What is Cij? It is the dollar travel cost of going from I to J. So what is this condition? This is essentially a no arbitrage condition. It says that the price in city I should be no larger than the cost of going to city J and buying it in city J. Right? So the constraints in the dual eliminate any incentive for somebody living in city I to purchase it from city J. Right? Because if you did, there would be an arbitrage opportunity. So the other interpretation for this would be, in the absence of a negative cycle, you can find arbitrage-free prices. Okay? Now, why this detour about shortest paths? Let's go back to the incentive compatibility constraints. There they are at the top. And now what I've done is I've rewritten them so that the prices are on one side and the interim allocations are on the other side. Now, if I fix the interim allocations, that system, the second inequality that you see on the slide, looks like this. Agreed? So I can associate with the incentive compatibility constraints a graph as follows. One vertex for every type. And I'll put an edge going from S to T corresponding to the incentive constraint where type T pretends to be type S, and the length of that edge will be this. And going in the other way, it'll be this. Now, if you give me an allocation rule, incentive-compatible payments exist if and only if what's true. That network has no negative cycles. Right? Now, what does it mean to have no negative cycles? Well, here's one particular cycle, a very simple one, S to T and back again. So this plus this had better be non-negative. Now, if you add this to this and make it non-negative, what does that say about calligraphic A? It essentially says that if T is bigger than S, then calligraphic A sub T had better be bigger than calligraphic A sub S. So one thing that you get out of the no negative cycle condition is that you must have an allocation rule that is monotone. Does that make sense? Now, I only picked out one cycle, right? The condition for feasibility is all cycles must be non-negative. So you might then ask, well, would there be additional conditions from cycles over more vertices? And the answer, it turns out, is no, because of the particular functional form for the edges. And you can check this. Look at a cycle involving 3 vertices. You don't get any more information than you get from just looking at a cycle on a pair of vertices. Right? So that's an outline for the argument that says incentive compatibility in this world is equivalent to the interim allocation rule being monotone. Okay. Now, what else do you get from this? Well, once you pick your allocation rule, what would the payments be? Well, the payments would be upper bounded by the length of the shortest path from the source to that type. Now, what would the choice of the source be? It would be the dummy type 0. Now, if your goal is to maximize expected revenue, what do you want to pick your payment to be equal to? You want your payment to be as large as possible, equal to the upper bound, but the upper bound is the length of the shortest path from the source to that particular type. So your payments are equal to the length of the shortest path from the source to that particular type. And since edge lengths are linear functions of the A's, that means the payments will be linear functions of the A's. Does that make sense? Okay. Now the last feature is this. As you change the A's, might you change the shortest path from the source to a particular type? Because as you change the A's, you're changing the lengths of the edges. As you change the lengths of the edges, the particular shortest path from the source to, say, type 7 could change. That's a possibility. Here is where the assumption that types are one-dimensional kicks in. Because the types are one-dimensional, it means the network you have is very special. What does it look like? Here's the dummy source, the dummy type. That's what the network looks like. Let me draw it out one more. And remember, the form of an edge length is this. So a little bit of algebra shows you the following. As long as these things are monotone, the length of the shortest path from the dummy type to type 1 is this. The length of the shortest path from the dummy type to type 2 is this. The length of the shortest path from the dummy type to type 3 is this. In other words, as long as the calligraphic A's are monotone, the shortest path remains the same. Its length changes, but the set of edges that make up that shortest path never change. It's always straight through the middle. Okay. And so that allows us to write down explicitly the payments as a linear function of the allocations. Now, as you move away from one-dimensional types, that's no longer true. If types were two-dimensional, imagine these nodes actually being on a lattice. Then the shortest path from the dummy type 0, 0 to some type over here, well, it could be along the diagonal. It could go along the horizontal and up. It could go up the vertical and along the horizontal. And then you can imagine all the combinations in between. Okay? So that case is much more difficult because you cannot tell a priori which is the shortest path. In Meyerson setting, because the types are one-dimensional, you know that as long as the allocation rule is monotone, then the shortest path is always 0 to 1 to 2 to 3 to 4, all the way up to t. And now if you do the algebra, it works out that the length of the shortest path to type t, or the payment to type t, is given by this expression. And what is this expression? It's basically the sum of these terms as you travel along. All that matters is there's some linear expression for the p's. Yes?
So in this case, is it also shortest path that goes straight from 0 to whatever it is? It should be at the same length.
So the answer is that could also be a shortest path. That's not ruled out. But you know that whatever A's you choose, as long as they're monotone, 0 to 1 to 2 to 3 will always be a shortest path. Okay? Now, in fact, you can also interpret what it means to travel along these. If you travel along this edge, then the incentive constraint that gave rise to this edge must bind at optimality. So another way to make this statement, and this is the way that Meyerson would say it, is that you're essentially assuming that the incentive constraints that link adjacent types bind. And as long as you satisfy those, then you automatically satisfy all the other ones. So if you put those pieces together, in the top I've replaced the payment variable by the linear function of the calligraphic A's. And if you do some rearranging, you get that expression over there, and what I have in braces is the virtual value. Those of you familiar with Meyerson will know that he gets this by integration by parts. And as some of my colleagues lovingly joke, it's not often you get to win a Nobel for doing integration by parts. I have eliminated the incentive compatibility constraints and replaced them with an equivalent statement involving only the calligraphic A's, that they be monotone. So notice I have a linear function of the A's subject to a bunch of monotonicity inequalities and the polymatroid constraint. If these didn't exist, I'd be home free, because I'd be maximizing a linear function subject to a polymatroid. Agreed? Okay. Well, let's ignore the monotonicity constraints. How do we solve a polymatroid optimization problem? We pick the variable with the largest coefficient and make it as large as possible. And then the next one. Agreed? Now, if I want to satisfy the monotonicity constraint, what do I want to be true? Yes, so how do I make life easy for myself? I make an assumption that makes the monotonicity constraints redundant. What's the assumption? Monotone hazard rate. So if I make the monotone hazard rate condition, notice if the coefficient associated with t is bigger than the coefficient associated with s in the objective function, the monotone hazard rate condition tells me what? T is bigger than s. Now when I apply the greedy algorithm, what do I know? I know that the variable I pick first has a higher value than the variable I pick second. Okay. Now, last catch. This gives me a solution in terms of the calligraphic A's. This doesn't give me the allocation rule, right? This only says something about your expected allocation. It doesn't say what the allocation rule is. But it turns out it's very easy to recover the allocation rule. Why is that? Because, as I said, think about the extreme points of a polymatroid characterized in terms of priority rules. So there is a standard trick that allows you to convert from this to an allocation rule. What's the trick? Take your optimal values for the calligraphic A's and interpret them as priorities. Here's the allocation rule. In any profile of types, give the object to the agent with highest priority. Now that's essentially Meyerson. Okay? Does that make sense? Yeah.
How can you know that the solution is going to satisfy the monotonicity constraints before you've given that verbal description of it?
Okay, so if I assume the monotone hazard rate condition, then I know that the coefficients are ordered in the same way as the magnitude of the types, right? And then if you think about the greedy algorithm for solving polymatroid problems, right? So if I use the greedy algorithm with this particular choice of submodular function, then the type which has highest objective function coefficient gets the largest value.
Why is that obvious? You're getting, well, there are two things involved, right? One is you got geos, the whole set.
So the answer is it's because.
The other thing is you have to divide out by these FTs, right?
Ah, very good. So you're right. There's a little piece of algebra here that you have to do to establish monotonicity, and I've skipped over that. Right? And that really is making use of the special form of this thing. But it's not hard. But it's not hard to prove. Okay. Okay. Now, what's the advantage of this compared to Meyerson's original approach? Well, if you want to add in extra constraints, it's now easy. So suppose you want to put in a budget constraint for agents. So agents cannot pay more than a certain amount. Well, you have a formula for the payments. You just put that less than or equal to the budget. So now you have an extra constraint involving the calligraphic A's, which comes from the budget. What do? Take it, the monotonicity constraints, up into the objective function with Lagrange multipliers, and then just as in Myosin, make up your own monotone hazard rate condition assumption. And then you have a simple mechanism to describe the optimal auction. Okay? Yes?
Maybe you could handle like asymmetrically distributed values.
Yes, you can, yes.
You have some order preservation in the virtual valuation, right?
Yep, that's all you need. So in fact, there is an extension of this to the case of asymmetric types. You can put in quota constraints. For example, no agent is entitled to more than 60%, and so on and so as long as the additional constraints you add in preserve the polymatroid you get here, you're home free. Okay, any questions? Yes?
This monotone hazard rate condition seems like we need it for this approach. Do we need it also for the results, or are there?
No, let's be careful. The monotone hazard rate condition is really a way of having to avoid dealing with the monotonicity constraints. Right? So in other words, I have a problem which is maximize a linear function, subject to a polymatroid, subject to a bunch of additional constraints. I know how to solve maximize a linear function subject to a polymatroid. I don't know what to do with the additional constraints. What's the response? Make enough assumptions to make the additional constraints redundant. Okay? Now, if you don't like that, something that people do, and I've never quite understood why this is exciting, but out of completeness I should tell you, supposing these constraints are not redundant, that means at optimality some of them bind. Take these constraints up into the objective function with Lagrange multipliers. Now it's a linear function subject to a polymatroid constraint. Okay. When you take these up into the objective function, you're going to adjust the virtual values by the Lagrange multipliers. That adjusted virtual value is called an ironed virtual value. So then I just say the optimal solution is give it to the agent with the highest ironed virtual value. I don't know how revealing that is, but you know, it's accepted. Okay, so you'll hear more about these kinds of things from Jason later this week. I just wanted to emphasize the role of the shortest path condition in the Myosin analysis, and also to point out how the polymatroid assumption there again allows you to guess the form of the solution fairly immediately. Okay. Now what I'm going to do is give you another application of the shortest path assumption, of the shortest path problem, and this is to the problem of rationalizability. Now in a sense, this is not a mechanism design problem. In fact, when you see it, you'll say, oh, this is a reverse optimization problem. But the reason I want to mention it is because the structure is essentially the same as the structure you see in Myosin or other mechanism design problems. So the result, although I put down the name Afriat, I'm actually going to describe a baby version of Afriat's theorem, but here's the setting. You have n observations. Now what is an observation? An observation is a vector of prices and a vector of quantities purchased at those prices. So the story you should have in mind is a single agent, and that agent gives you n observations about what they purchased at various prices. I want to know whether those observations are consistent with the following: that the agent has a concave utility function which is quasi-linear and locally non-satiated, so that what they purchased at a particular price is a solution to this optimization problem. Now, what is this optimization problem? It's pick the bundle X that maximizes your utility plus the amount of money left over subject to your budget constraint. Where is the quasi-linearity assumption coming in? Money appears here in the constraint and also in the objective function. Does the question make sense? Okay? I have the observations, and I want to know whether they can be explained by a particular class of preferences. Yes?
What's S again?
S is, so think of this as the amount of money you spent on the goods you purchased, then S would represent the money left over. And because your preferences are quasi-linear, the money that you have left over should also enter your objective function. Okay? Now, Afriyat's version of the theorem, preferences are not quasi-linear, so that you wouldn't have this. Okay? Okay. So how do we know whether the preferences can be rationalized in this way? Well, supposing at the price vector pi, the bundle xj was feasible. In other words, at the price vector pi, you had the money to buy the bundle xj. What does that tell me? It tells me that your utility for I must be larger than your utility for j. Right? If at the time you bought an apple, you could also have afforded an orange, then you must prefer the apple to the orange. Yes?
Is there a strict concavity of you?
I have not assumed strict concavity, but if you want, we can put in strict concavity. Right, so notice what I have. I have the utility for your bundle xi. What is b minus pi xi? It's the money left over. That has to be more than your utility from consuming bundle xj, plus the money left over if you decided to consume the bundle xj. Now, what am I after? I'm after the u's, right? The u's are my variables. Let's rewrite the system. Remember, the u's are the variables. What's on the right-hand side we know, because we observe that. So in a sense, what is the question I'm asking? Is that system feasible? Now, if you look at it, this is the dual to the problem of finding a shortest path. So you can proceed in this way and write down a bunch of inequalities of this kind. I've replaced u of xj by yj. So here's the shortest path problem. This system is feasible if and only if what's true. The underlying network does not have negative cycles. Okay. Everyone with me so far? Yes?
But for after, we don't need to show that, we don't need to find the u, right? We just need to say that exists in u.
We just need to show that they exist to you, right? Now, you've got to be careful here, which is the yj's and the yi's only pin down the utilities at observed bundles, right? There's a missing step, which is it's not enough for me to say, look, I can put down utilities for the observed bundles. I've also got to tell you what your utility is for the bundles that I never observed you purchase, right? So that's still missing from this system. Okay. Now, in the absence of negative cycles, I know that this system is feasible. And what I'd like you to pay attention to is if you look at this, this is a lot like the incentive compatibility constraint in myosin. Right? And in a sense, you shouldn't be surprised because the only thing I'm doing is I'm changing which variables matter. In myosin, the quantities are fixed, and I'm choosing the prices so that you make rational choices. Here, I'm choosing the prices and the quantities and asking what your preferences must be in order for those choices to be rational. Right? That's the only difference. But mathematically, it's the same structure. Okay, so suppose there are no negative cycles. So as I said, here's the way you'd construct the network. If there are no negative cycles, then you have a solution for the yj's. So I can give you your utility for each observed bundle. Now, how do I fill in your utilities for all the other bundles? I essentially say the utility X for any other bundle is this. Okay. So basically, there's a way to interpolate between the utilities of the bundles you've pinned down to the utilities of bundles you haven't observed. And the thing I'd like you to notice about this is that this is an affine function. So this is the minimum of a bunch of affine functions. So that's piecewise linear concave. Okay? Now, there's some algebra in order for you to check that the preferences that you get from this are consistent, but it's not really hard because essentially what you're really doing with this construction is in your network, you're adding in the other bundles that you didn't see, and you're choosing the length of the shortest path so that they're well behaved, so you don't add more negative cycles. Okay? And so this, if you like, is the baby version of Afriat, just directly from the shortest path technology. Okay, the other reason I put this example of rationalizability up is because I think there are a host of interesting questions regarding rationalizability, some of which have been looked at and others which haven't. So here are some examples of things that have been looked at. Sometimes people will ask whether the observed purchase decisions can be rationalized by a more restrictive class of preferences. So not simply concave, but additively separable concave. It's not hard to do that. More elaborate situations are where you're observing the purchase decision not of a single individual, but of a group or a household. So I see what a household purchases at various prices and vectors. And now what I'd like to know is whether I can rationalize the preferences of the individual members of the household. That's again a line of work that has been looked at extensively. What is more interesting to my mind is what happens if people are making choices that are not quite rational. So here's what I have here's an idea, here's a thought. What if the problem of choosing the utility maximizing bundle is NP hard? There is no reason to suppose that in general the consumer is making the correct choice. So the observed purchase decisions you see are not the optimal solution to some utility maximization problem. Okay, so how did the hypothetical consumer choose the bundle? Well, let's suppose they chose it using some heuristic. Fix the heuristic. So here's the question. When can the observed choices be rationalized by a particular heuristic? Does that make sense? Now, this is a little different from the kind of questions that behaviorists would ask. Behaviorists would look at non-standard preferences. So you could think of preferences that are not, maximize a concave utility function, that are non-standard, and then ask when is observed behavior rationalized by non-standard preferences. So here I'm assuming the consumer has well-behaved preferences, but the problem of choice is a hard one. So the errors that we see do not come from the fact that they have incorrect preferences or they're irrational. The problems that the observations we see are the result of cognitive constraints. How would you rationalize observed behavior? Does that question make sense? Yes?
They do like the optimization problems and cost of computation.
So that might be one possible theory that you could in principle think about how you would rationalize. Okay, so I have no fixed view on the right way to do this, other than I can't think immediately of the right way to do this, but I think of this as important a question as asking whether choices can be rationalized by non-standard preferences. Okay? So I'm saying, look, there's another reason why choices may not be optimal that has nothing to do with non-standard preferences. It's that the computation problem associated with choice is difficult. Okay? Any questions? Yes?
Along these lines, I think the type of difficult for a person is the same as what would be difficult for an algorithm, for a machine.
You're right. That's the assumption I'm making, and you could legitimately argue with that because sometimes what we think of as difficult depends on the model of computation that we use, right? So, as an example, we don't think of finding the root, say, of a cubic as really being difficult, but in at least one model of computation, you have to specify a degree of precision, and then the length of the computation grows badly with the degree of precision, right? So yes. So it's worth thinking so it's worth also thinking carefully about what we mean by computationally difficult. That would depend on the model of the model of the way in which you choose to count count steps. Yeah. Yes.
Related to the previous question, does it matter if the difficulty comes from computational, like NP hardness or some other, or for some reason, maybe I don't know, they just don't have enough, maybe even if it's in P, but they don't have enough patience to compute, they don't really want to compute the optimal one, they're satisfied with computing something close to optimal.
Yeah. Okay. So I would lump that under behavioral models, in the sense that there's a long tradition of trying to think about what satisficing means. In other words, people will compute to the point until it's good enough.
But does it matter for what you're trying to
Right. So it is possible. It is possible that maybe there is no good way to distinguish between satisfying and using some and between the problem is NP hard and I'm approximating. So again, I have no way. Again, this is why I think it's an interesting question whether you might even be able to distinguish between two competing models of choice based on observed data.
I don't think that they're even distinct. Difference. Like given a problem, like every instance of a particular problem cannot be NP hard. It's just a finite instance. So and I compute the solution up to a certain degree of accuracy. It's just a matter of interpretation. Why?
Okay, so the reason why I'm reluctant to yield on that is because I find the notion of satisfying problematic, because you can sometimes interpret satisficing as being optimization subject to constraint, subject to it being good enough. But we also know that we can take problems that are well solved, add in a constraint, and then they become hard. Right? So if the argument is that somehow we might be able to explain observed choices using satisficing, it only makes sense if the way you choose to formulate the satisfying problem is easy. Am I making sense there?
Just that every particular, just a class of problem can be hard, but every particular instance
Okay.
is never hard. It's just a finite instance. So why? I mean, the reason I stopped.
Oh, I see. Okay, so the claim here is that then that's fine. So then you're saying the model of choice should be something like this, which is I have a cost of computation, right? And then I'm going to trade off that cost of computation against the value that I get for each additional, right? Okay, so perfectly plausible model. Then my question would be, can I rationalize? So can you tell me how to rationalize that? So I give you observed choices, and now what your model would have to tell me, this is the implied cost of computation in order to explain these observed choices.
Can't you, I mean, you have a linear program here you're trying to optimize, right? So can't we find a way to do that?
So the difficulty now is the optimization problem is you've got quality of solution plus the cost of computation in the objective function, right? Now, I don't know whether that's a well-behaved optimization problem. Okay, it's going to depend on how you choose to count, how you choose to evaluate the cost of computation. Okay. Yes?
So one way you could see how close you get to rationalize to actually being rational is, you know that for a finite set of goods, you have to satisfy God if your choices are rationalizable. And I know a couple of experiments where they change the budget lines so that they keep intersecting, and then you get a measure of how often people make choices that are
Yes, so actually, yes. So there's another line of work which is supposing your observed choices are inconsistent with maximizing a concave utility function. Is there a sense in which it is close to being consistent, right? And so there was so there have been a number of suggestions going back all the way to Afriat for approximate notions. Some are too permissive in the sense that, well, almost anything looks rational, and some are overly restrictive. So even that question is not completely settled either. And actually, so on whether you should look at everything as being sort of, I get tired after doing a bunch of computations, I would say no, because you can think of other situations where there seem to be well-known heuristics that people use, like greedy. So knapsack problems, it's not uncommon for people simply to use the obvious greedy algorithm, which is pick the object with the largest objective coefficient to weight ratio.
Yeah, but this has nothing to do with being NP-hard. People use heuristics also for
Right, but that's right. So you could ask, could observed choice be rationalized by a particular heuristic, right? Yeah. Okay. Let me now switch gears entirely towards the allocation of indivisible objects. And because I think allocating indivisible objects turns out to be one of the more difficult problems. So the first thing I want to emphasize is nothing is really indivisible. When we say that allocating an indivisible object is hard, what we really mean is that if we physically divided the object, value would somehow be destroyed. Okay? I can divide Jerusalem. You may not like it, but I can. Okay? Now, if you look through history, I think there are about 8 different ways that you see people attempting to divide indivisible objects. One is through actual physical division, and the story of Solomon and the baby is sort of the obvious one that comes to mind. The other is to hold the asset in common. So if you want a particular story to illustrate this, imagine 2 heirs competing for a painting, and instead of the painting being kept in one heir's apartment or the other, it's kept on a common corridor that links the 2 apartments, for example, right? That would be holding in common. The other is compensation. One party compensates the other for the asset, and compensation doesn't have to be money. It could be for exchange of something else. Other examples are exchange for something divisible. In other words, the asset is sold off for money, and then the money is divided up between the claimants. A fifth way is what's known as unbundling the attributes. So you might give ownership to one, but restrict the ways in which they can use the asset. So this has been done on a number of occasions. The Camp David Accords, for example, regarding the disposition of various pieces of land, ownership to one country, but restrictions on how they could use it. Same technique was used with Spitsbergen when it was returned to Norway. The Norwegians were allowed ownership of Spitsbergen, but fishing rights were shared between the US, Russia, and I think Sweden. And the 3 that I want to talk about are lottery, rotation, and removal. So lottery is sort of the obvious thing, which is you randomize. Now, there are sometimes objections to the use of lotteries because a lottery, while ex ante fair, will be ex post unfair. So we have a single object, we both have an equal claim to it, we agree to flip a coin 50-50. Before the outcome of the coin flip, it looks fair, but after the fact, one of us feels regret. Okay? That said, lotteries are not uncommon. And it is not the case that people use lotteries only for unimportant objects. So an example of the use of a lottery to allocate an indivisible good or rights, and these rights are relatively significant, actually comes from Australia in around the 1800s. So many of you will know that what we think of as modern-day Australia was founded as a penal colony for the British. And one question you might have is, what do you do with the convicts in Australia? And the answer is, they were sent to Van Diemen's Land, now called Tasmania. And conditions in Tasmania were so harsh that convicts were prepared to do almost anything to get off the island. And here is what they did. One way of getting off the island was the following. A murders B, and C claims to be the witness. Then A and C are sent back to the mainland to be tried. Okay? So, clearly the problem is who gets to be A, the murderer, who gets to be B, the victim, and who gets to be C, the witness. And this was decided by lot. Okay? So this is an example, I think, of a sort of a significant right that is in some sense indivisible, that is allocated by lottery. Okay? Now, some more extreme cases of lotteries, and this is related to physical division. When India was separated from Pakistan, requirement of the separation was that the assets held jointly by the colony were to be divided up between the two countries. So monetary assets were divided in proportion to population. So roughly 80% India, 20% Pakistan. Now, what do you do about indivisible objects? Well, certain indivisible objects like chairs, tables, and chamber pots, there were enough copies of them that they would do 80% of one, 20% of the other. What about books? So on books, interestingly enough, they chose 50-50. It was not divided in proportion. So dictionary, A to L to Pakistan, M to Z to India. Okay. What do you do about books for which there was only a single copy, Alice in Wonderland, for example? Believe it or not, they ate up a whole day arguing about which nation had the greater need for a copy of Alice in Wonderland in the National Library. Okay. Going back to the book example, the library example, in Belgium, and this is part of the folklore for most economic theorists, there used to be a University of Louvain, but then during the language wars it was divided into two, a French-speaking and a Flemish-speaking university. So what were they going to do with the great library at the university? Well, they decided every other copy. So you go down the shelves, copy number 1 to the French institution, volume number 2 to the Flemish institution, volume number 3 to the French, volume number 4 to the Flemish. Notice there was no attempt to say, well, at least the books in French should go to the French institution, or the books in Flemish should go to the Flemish institution. And then they were allowed to trade. Okay? So here you had physical division, and then in some sense exchange afterwards. Okay? Now, related to lottery is also rotation, because you can sometimes interpret probabilities as being timeshares. So instead of flipping the coin 50-50 to see who gets the painting, perhaps I get the painting for the first half of the year and you get the painting for the second half of the year, right? So there's a way to interpret lotteries in terms of timeshares. Last method that you sometimes see is simply destroying the item altogether. Right. So again, India and Pakistan is a classic example of this. Ceremonial coaches used by the viceroy had to be divided between India and Pakistan. 6 were gold, 6 were silver. They agreed on a coin flip. Whoever won the coin flip got the gold ones, the loser got the silver ones. India won the coin flip, got the gold ones, Pakistan got the silver ones. But there was something known as a ceremonial horn. There was only one of these, and the assistant to the viceroy decided another coin flip would be too problematic, because if it went to India, Pakistan would complain, so he simply walked away with it. Okay, so that's an example of removal. Okay. Now, there are some cases where dividing indivisible assets we have a lot of positive results for. And that case is typically what Eva has already talked about, unit demand. So there are a bunch of objects and a bunch of agents, and each agent is interested in consuming at most one of the objects. So here is a simple setup. So here's agent 1, here's agent 2, here's object 1, here's object 2. Now, supposing the objects were divisible, and I've suppressed any information about preferences because they're not relevant for the point I wish to make. Supposing the objects were divisible, and depending on the preferences of the agents, you decided that the following division was appropriate. I don't particularly care why you like this division. You think this division is appropriate. So the first object is divided in two and given to the two agents. The second object is divided 75%, 25%. Okay? Now, if I suddenly come back to you and say, wait a minute, these goods are not divisible. They're actually indivisible. So you can't split them. What might you do instead to mimic the fractional allocation? Well, an obvious thing to do is to interpret these as probabilities, right? Now, the naive interpretation might be, oh, it's easy. Flip a coin to decide, an unbiased coin to decide who gets this, and then flip a weighted coin to decide who gets this. Now, the reason why this is incorrect is because if you do things that way, then you're not actually giving this agent a 75 to 25% chance. You're not actually giving this agent a 75% chance at object 2. Does everyone see why that's the case? Because if you flip the coin on this first, and let's say it goes to agent 2, remember each agent only wants to consume one object, then this object automatically goes to agent 1. So the naive way of flipping the coins will not work. You're not giving them the probabilities in some sense that you promised. Right? Now, in this setting, there is something called the Birkhoff-von Neumann theorem, which makes life very easy. It says, not a problem. If these are the splits that you want, there is an equivalent way of specifying a lottery over all ways of assigning objects to agents that will match those fractions. Okay? So the Birkhoff-von Neumann theorem says, the naive way won't work, but there is a way that will work that will implement an allocation that matches these fractions. Yes?
But if each agent only wants one item, so what does it mean that agent 2 gets half of item 1 and 3/4 of item 2?
No, remember I said initially suppose I should have been more careful. I said initially suppose the goods were divisible and no agent wants to consume a total quantity that exceeds 1. Oh, is there an arithmetic? Oh, I'm sorry. Thank you. Okay. Does that, okay. Okay. Yeah, sorry. So maybe I should go and say this again. So now, right, you'd want to interpret these as lotteries, right? Now, your problem is if you flip a coin to decide who gets this, whoever gets this, then the other one by default gets the other item. Right? And it's not obvious that you can necessarily flip the coins in the right order so as to give everyone the probabilities that you promised them. But the Birkhoff-von Neumann theorem tells us we can do this. Now, what drives the Birkhoff-von Neumann theorem is one simple fact, which is every agent wants to consume no more than one unit. That's really what makes life easy here. And what happens if sorry, I jumped ahead here. I could interpret this as lotteries, but another interpretation of Birkhoff-von Neumann is in terms of timeshares. Right? So rather than flip a coin, I say that you get this object for this fraction of the year, you get this object for this fraction of the year. And there is a way to assign the fractions so that there is no conflict on any of the objects. so that you're not allocating the same object to two people during the same time window. Now, all of that is driven by the fact that agents have unit demand. They're interested in consuming at most one unit. Right? Okay, what happens if they're interested in consuming more than one unit? In that case, Birkhoff-von Neumann does not apply, and there is no natural generalization. So what I'm going to do now is I'm going to say that if you're going to accept something like removal, there is still a way to allocate objects in the way that you might like. Right? That's sort of the rough message. Now let me be specific about the assumptions and the kind of results. Yes?
So if people have capacity larger than one, why can't you create a hypertext graph where you make many copies? So if I have capacity of 2, I can make 2 copies of me, do Birkhoff von Neumann, and then,
So the answer is if everyone has the same capacity, then I could do it. But what if they have different capacities and the preferences are more complicated than the ones that I just described? Is that?
If there's different capacities, you can still do it. I don't know I'm trying to understand what setting you...
So I'm now going to be more specific about the kinds of settings I have in mind. So there are 3 possible settings that the machinery will go through for. Setting number 1 is no agent wishes to consume more than k goods. Okay? But they will have preferences over bundles of size up to k. Okay? Now, you may not like assumption number 1 because basically it introduces some kind of non-monotonicity. Because it says, well, once the bundle goes beyond size k plus 1, your value for it goes to 0. If you don't like that, there's assumption number 2, that your utility for a bundle is basically the maximum utility you obtain for any subset of that bundle of size at most k. Okay. There's a third assumption, which is another way of phrasing this, which is there's a partition of the objects. Each element of the partition is of size at most k, and your utility for a bundle is given by this. So within the element of a partition, the utility can take any form. So you can allow complementarities and substitutes, but across the partition, it's additive. Now, if you want a story to go along with that, think of bands of spectrum. I worry about interference from neighboring pieces of spectrum, but not from pieces of spectrum far away. So my utility for 2 non-interfering portions of spectrum is additive, but my utility for 2 interfering portions of spectrum will be subadditive. Okay, so these are the kinds of preferences we have in mind. So now let me give you an example of the kinds of results that we would like that we get. So imagine you have a set of distinct goods, and S sub j is the integral supply of good j. Assume no agent wishes to consume more than 1 copy of any particular good. This is just for accounting purposes. What's the result? When agents have quasi-linear preferences and k-unit demand, in other words, the preferences look like one of these things, then there exist valuation prices where the excess demand for any good is at most k minus 1. Now, what's the interpretation of this? The interpretation of this is only interesting when k is much smaller than Sj. Because this says, in a sense, that valuation prices approximately clear the market. Now, why do I care about this? Well, because there are a number of proposals for running combinatorial auctions, which first begin with a clock phase, which is designed to find valuation prices. And the intuition is that in that clock phase, you get a lot of price discovery. And then after that clock phase is over, then you run a full-fledged combinatorial auction. Right? So this theorem would suggest that if the clock phase is run right, then most of the market should clear by the end of the clock phase. Okay? Another way to interpret this result is it says, that K, in a sense, determines the degree of complementarity there are in preferences. When there are complementarities in preferences, then valuation prices that support the efficient allocation do not exist in general. But if the degree of complementarity is in some sense small, and that's measured by this K unit demand assumption, then it says valuation prices are there exist valuation prices that approximately clear the market. Here's a second application. G is a set of distinct classes, and Sj is the integral number of seats in each class. No agent wishes to consume more than one copy of any good. Okay? And under the K demand assumption, here's the result. There is a lottery over assignments of classes to agents that is approximately efficient, ex-ante envy-free, asymptotically strategy-proof, and such that ex post each assignment consumes no more than Sj plus K minus 1 seats. In other words, again, the excess demand does not exceed K minus 1. Now, what's the interpretation? Imagine that the typical class has about 25 or 30 seats, and you're only interested in taking 4 classes a quarter or a term. Then your K is 4. It says that the excess demand in any class would be at most 3. So, you can either stick in 3 extra seats, or you can hope that not everyone is present every day, or you could go back and remove 3 seats and run the allocation, knowing at the end of the day you'll have enough, you won't exceed the actual capacity of the class, and that's what I mean by removal. Okay? So once again, if K minus 1 is small, it quantifies the fact that only a small number of goods have to be removed in order for you to achieve whatever equity or efficiency objectives you have. Does that make sense? Okay. Now, how does one get results like this? The answer is shameless arbitrage. And so the arbitrage is we use a technique that is now common in computer science called iterative rounding. Shameless because those of you who've seen this results are probably saying to you, has he no shame? And the answer is no. I'm simply going to take these results and relabel them. Right? So here is the setting. N is the set of agents. G is the set of distinct goods. And Sj the integral supply of the goods. Again, no agent wishes to consume more than 1 copy of any good. Now here's the variables. Xi of S is 1 if the bundle S is allocated to agent I and 0 otherwise. Now, an assignment or an allocation of bundles to agents is feasible if it satisfies these 2 constraints. So no agent is given more than 1 bundle, and the set of bundles that share an object in common that are given out must be less than or equal to the available supply of that object. Now, what does iterative rounding do? It takes as input an extreme point to the linear relaxation of this. So pick any objective function you like, maximize over this, that gives you an extreme point. So that's your input. And the objective function we're going to pick is one consistent with the assumption of K valuations. So utilities of bundles of size larger than K, I'm going to give them value 0. And then what you're going to do is you're going to take that extreme point and you're going to round it into a 0-1 solution that satisfies this constraint. No agent gets more than 1 bundle. And you're going to violate the supply constraint, but by this much. Okay? That's the iterative rounding method. Okay? So what is it? Start with your extreme point. Any variable that's 0 in the extreme point, throw that away. Any variable which is set to 1, fix it at 1 and then get rid of it thereafter. Now you have to adjust the inequalities as you go along, because the variables that are 0 you're removing, the variables that are 1 you take over to the right-hand side, so that you're adjusting this and removing the corresponding constraint here. In the system that remains, pick a new extreme point in the same way, by maximizing the same u over that reduced polyhedron. Now, at some iteration, you must reach an extreme point where no variable is set to 1. So all the variables are fractional. In that case, you can prove that the following must be true. In other words, there must be a good where the number of agents who get a positive amount of that good is no more than this. Okay? That's the thing that you have to prove. Okay? For every such good, throw that constraint away. Repeat until every variable has been set to 0 until you've got a solution. Okay. Does the procedure make sense? Okay. Now, what's the claim? At each iteration, this holds. Because the moment you get a bundle, I throw you out. Right? I give you your bundle and you leave. At each iteration, I'm solving this. I have the same objective function, but I'm throwing away constraints. So I'm solving a relaxation at each iteration. So the final rounded solution must have an objective function value larger than the objective function value of the initial extreme point solution. Now, what about the constraints that I threw away, these ones? Well, this says basically, if I take any agent who is assigned a bundle that contains J, and I give them that bundle, the excess demand for that bundle will be at most k minus 1. So that means all those capacity constraints I threw away, I know at the end of the day, will satisfy this. Okay? And how do we know this is true? The following lemma from Kirali, Lau, and Singh. Okay? So I said, we just reworded it, and it tells us that there exists such an. In other words, if there are no variables set to 1, then you've got to have one of these. One of these things has to be true for one. This has to be true for at least one of the goods. All right? Given that time is short, I'll skip the proof. Our proof is different than the original proof. Here's a new result, which is take any fractional solution of this, it can be written as a convex combination of integer solutions that satisfy this. So in other words, any fractional allocation you like can be written as a lottery over integer allocations, where the integer allocations have an excess demand of k minus 1. So pick your favorite fractional solution because it satisfies whatever equity or efficiency properties you like. It can be implemented so as to preserve ex ante those equity and efficiency properties at the cost of violating the capacity constraint by k minus 1. So now let me close with, here are some simple things you can do. Supposing you wish to allocate the object so as to satisfy what's known as max-min share. Okay. So you want a choice that ensures that the rounded solution gives to each agent a bundle they prefer at least as much as their maxi-min share. How do you do this? Fix an H, throw away any bundle that an agent ranks below H place in her preference ordering. So you're only keeping the bundles that an agent ranks H or higher. Okay? Let H be the smallest index for which there's a feasible fractional way to assign everyone a bundle they rank H or higher. So that's your initial fractional solution. And then the result about the lottery says, well, there's a way to express that solution as a lottery over integer solutions. And in that lottery, everyone is getting a bundle that they rank H or higher. But the cost is you violate the capacity constraint by k minus 1. Here's another one. Maybe you want an allocation that is envy-free. So you put in this constraint. Maybe you want, in addition, you want envy-free and maximize efficiency. You get a fractional solution. And again, that lies in that polytope. So again, you can express it as a lottery over integer allocations, which give you the same efficiency and ex-ante envy-free at the cost of violating the capacity constraint by k minus 1. And where does strategy proof come from? Well, as the number of agents gets very large, you're choosing as your starting point an allocation that maximizes this. So as the number of agents gets very large, the impact that any one agent can have by changing their preference on the solution to this is very small. Envy-freeness therefore says that they cannot gain by manipulating their preferences. So asymptotically, you get strategy proofness. Okay? So the point here is not very much effort. Gives you a whole bunch of results for free that you can interpret as generalizations of Birkhoff-von Neumann to the case where agents have preferences not over single items, but over bundles. Okay? And I think I'm out of time here, so I should end and just answer questions if there are any. Yes?
So going back to the case of the visible goods,
Yep.
sometimes in mechanism design you want to maximize a non-linear function when you have non-risk neutral agents.
Yep.
That's your method with one matrix that apply there by doing something variable, for example.
Actually, so actually what makes everything work is that agents are risk neutral. Because if you notice in both the Myason's example today and the example with allocation and inspection yesterday, the way both of those worked was by eliminating the incentive compatibility constraints. And the reason you could eliminate them is because they were linear inequalities, so that there were simple operations you could perform to eliminate them altogether from the problem. When you have utility functions, then the incentive constraints are no longer linear. So you don't have a linear program to begin with. Does that? Okay. So the problems with risk aversion or non-risk neutral, very difficult. And the only ways I know of dealing with them. Okay. Actually, there's a recent result by Carl Schmedders that I think will be useful, which says that in some of these cases, you may be able to reformulate the problem as a semi-definite program. Okay, so when the incentive constraints are not linear, provided you have the right restriction on the utility functions, and I forget what the restrictions are, you may be able to reformulate the mechanism design problem as a semi-definite program. Okay. However, he doesn't have any results to suggest at the moment that these semi-definite programs you can sort of look at and pick out a nice, pick out qualitative properties of the optimal solution. Okay. Okay. Thank you very much for your attention.